It's Tuesday night and you are studying for a test. You have a notebook, the textbook, and flashcards. You have so much information that you feel overwhelmed. In the same way, you, like the student in Figure 1, could be easily overwhelmed by all of the data gathered from scientific investigations. To be useful, data must be organized. But how? In this section, you will learn some of the same methods that scientists use to make information easier to interpret and understand. Creating a data table. For several years, a teacher has been investigating the amount of exercise his students get weekly. The students gather information about the total hours of exercise they get each week. The first step that the teacher and the students take in organizing the data is to fill in a data table. A data table has two columns, as shown in Figure 2. The first column lists the independent variable, the factor or parameter that the investigator can change. In this case, the class chose to study the total number of hours exercised each week for 5 weeks. So, the independent variable is the week. If the class chose to study the total number of hours exercised each month, the independent variable would be a month. The second column in the data table lists the dependent variable. The dependent variable is the factor that changes in response to the independent variable. It is the variable that the scientist measures. In Figure 2, the dependent variable is the total number of hours exercised. It changes with the independent variable. So, the hours exercised change every week. Variable and controlled parameters. When you design an experiment, you have controlled parameters and variable parameters. Controlled parameters are factors that stay constant throughout the experiment. Variable parameters are factors that change or vary throughout the experiment. If you want to explore the relationship between two factors, such as mass and volume, then those factors are your variable parameters. All other factors, such as temperature and the material you study, should be kept constant and are your controlled parameters. Creating a graph. Data tables help you organize data. Graphs help you understand and use that data. Graphs make it easy to identify trends and make predictions. Students studying the amount of exercise they get each week use their data table to graph the total number of hours exercised over a 5-week period. Axes. Figure 3 shows how to make a graph. First, use a data table to determine the graph's axes, singular axis. An axis is a reference line that forms one side of a graph. A graph has a horizontal x-axis and a vertical y-axis. The x-axis usually represents the independent variable in the data table. The y-axis usually represents the dependent variable. In a graph of the number of hours exercised in a 5-week period, the x-axis represents the week, and the y-axis represents the number of hours exercised. Each axis is labeled with the name of the variable that is represented. Range. Each axis has its own range. To find the range, subtract the smallest value of a single variable from the largest value of the same variable. For the exercise data, the range of the independent variable, the week, is 5 weeks. Therefore, the x-axis must cover at least 5 weeks. The range of the dependent variable, the number of hours, is 53 minus 40 equals 13. Thus, the y-axis must have room for at least 13 hours. Scale. The next step is to decide the scale of the graph. Each axis has its own scale. The scale is the size that is used for each box or grid mark on the graph. For the exercise data, we can choose a scale of 1 week for each grid mark on the x-axis. For the y-axis, the grid marks can be placed at intervals of 10. The scale should be chosen such that the graph spreads out to fill most of the available space. Data points. Now, the data points need to be plotted. You plot the data points by putting a dot on the graph for each pair of data in the data table. Sometimes a line of best fit is needed. Most graphs of data or observations are not drawn dot to dot through the data points. A line of best fit, such as the one in Figure 4, is a smooth line that is drawn to fit or to include some but not all of the data points. The smooth line without sharp turns or sudden bends shows the pattern described by the data. The line of best fit also shows how the data differ from the pattern. Labels. The last step is to give the graph a title. The title helps people recognize what the graph describes. Scientists often include the independent and dependent variables in the title. Patterns shown by graphs. When you graph data, you can identify what the pattern or trend of the data is. A trend shows the relationship between the two variables studied in the experiment. Graphs make it easy to tell if something is increasing, decreasing, or staying the same. A straight line can sometimes be used to show the trend of data on a graph. A graph in which the relationship between the independent variable and dependent variable can be shown with a straight line is called a linear graph. Sometimes the relationship between the variables studied is not a straight line, but a smooth curve. Any graph in which the relationship between the variables cannot be shown with a straight line is called a nonlinear graph. Graphs allow scientists to determine if the relationship between the variables is direct or inverse. If a graph shows that the dependent variable increases as the independent variable increases, the relationship between the variables is direct. If one variable increases while the other variable decreases, the relationship between the variables is inverse. Figure 5 shows two nonlinear graphs, one of which has a direct relationship and one of which has an inverse relationship. Using computers to create graphs. Computer technology can be used to make organizing data easier. Computers help scientists collect, organize, process, and display large amounts of data. In Figure 6, a doctor is recording data on her handheld computer. With this tool, she is able to gather data rapidly and as needed. Specially designed software makes appropriate graphs from lists of data. These graphs can be quickly examined to find patterns and relationships between the variables. The instant feedback provided by computer technology allows scientists to make mathematical representations of large amounts of data as they are collected. One way to analyze data is to use mathematics. Mathematical models in the form of computer simulations can answer questions about how rockets, such as the one in Figure 1, will fly and react to different conditions before the rockets even leave the ground. Why mathematics? Just like making observations, conducting experiments, and organizing data, mathematics is used to answer questions. Mathematics helps determine important properties of substances, such as area, volume, and density. Mathematics also allows scientists to understand and sum up a lot of information. As a result, scientists can make predictions. For example, a meteorologist gathers data on hurricane movement. Mathematics helps her to see patterns in the data. Then, she uses these patterns to predict where future hurricanes might hit land. There are scientists in every country around the world. They speak many different languages. Mathematics is often called the language of science because it allows scientists to easily share their findings with each other in a language that everyone understands. Numbers. Accuracy of data. When scientists conduct experiments, they want to collect accurate data. In other words, they want the values to be correct. If you place 525 grams on a balance and get a mass reading of 450 grams, your reading is not accurate. Some reasons why a value is inaccurate include using broken equipment, using the wrong tool, or using a tool incorrectly. Choosing tools and using them correctly. You have probably made measurements using the tools shown in Figure 2. Using a graduated cylinder to measure volume can provide a more accurate measurement than using a measuring cup found in a kitchen. But your data will still be inaccurate if you do not read the volume at the bottom of the meniscus at eye level. Likewise, to get an accurate reading using a ruler, you should look straight down on the end of the thing you are measuring. If you move your head to either side, you will get a slightly different measurement. Reproducibility of data. Imagine that you and a friend do an experiment using the same procedure and equipment. You'd expect to get data that are very similar. When scientists conduct investigations, they want their results to be able to be repeated or reproduced by other scientists. If the data are not reproducible, then there is no way for the results of the experiment to be supported and accepted by other scientists. Data must be reproducible in order for other people to agree with your conclusions. Describing the entire set of data. When scientists analyze data, they often find it helpful to use a single number to describe the entire set of data. 3 terms that are used for this purpose are mean, median, and mode. Figure 3 shows how to find each one. The mean, or average, is found by adding all the data points together, then dividing the sum by the total number of data points. The median is the value of the data point in the middle when the data are placed in order from smallest to largest. The median is especially helpful when one data point is much smaller or larger than the rest of the data points, as in week 9 below. The mode is the number that appears most often in a data set. Slope of a line. What do you think of when you hear the word slope? You might think of how something slants uphill or downhill. Figure 4 shows a skier moving down a slanted mountainside. Imagine drawing a straight line under the skier that runs along the mountainside. The steepness of the line representing the slant of the mountainside is called the slope of the line. In math, slope is defined as the degree of slant of a line. Calculating slope. To calculate the slope of a line, it is helpful to use the terms rise and run, as shown in Figure 4. The rise represents a vertical change. The run represents a horizontal change. For a line on the coordinate plane, the change in y, or the rise, indicates the number of units moved up or down. The change in x, or the run, is the number of units moved to the right or left. Slope is calculated by dividing the vertical change, the change in y, by the horizontal change, the change in x. In other words, the slope of a straight line is found by dividing the rise by the run, often described as rise over run. Using slope to analyze data. The slope of a line graphed from data can help you analyze the data. Look at Figure 5. 3 sets of data result in 3 different lines, each with a different slope. For each line, the value of the slope between any 2 points on that line will be a constant number. Here, the slope, rise over run, represents the speed, meters over seconds, of an object moving at a constant rate. Figure 5 shows that slope can have a positive, negative, or 0 value. The slope of all horizontal lines is 0. Slope as the constant in y equals kx. Scientists sometimes find that their data form a straight line that includes the point that has x and y values of 0. They can then use the equation y equals kx to represent their data. Figure 6 is a graph representing the density of lead. Here, y represents measurements of mass, and x represents measurements of volume. Then, k represents the constant term, which is the slope of the line. The slope of this line, rise divided by run, represents the density, mass divided by volume, of lead. If you rearrange the formula for density into the form y equals kx, the equation is m equals dv. So, density is the constant k, which is the slope of the line. Comparing linear and nonlinear graphs. The lines on a graph can help you draw conclusions about your data. The slope of a straight line shows how much one factor, y, always changes in relation to another factor, x. A straight line shows that a constant linear relationship exists between the factors you are studying. In other words, y always changes the same amount in relation to x. But what if your data do not form a straight line? Many relationships that scientists study are not linear. In a nonlinear graph, each unit change in one factor, y, does not always bring about the same change in another factor, x. The graph of this relationship will be a curve instead of a straight line. So, there is a nonlinear relationship between the factors you are studying.